Hello, welcome to this lesson of our study of integral equations. Okay, so in this lesson we go through what we mean by the Green's function and how to construct the Green's function from a boundary value problem. Okay, so this is really important because this is one of the methods that we can use to solve a Fredom's integral equation, and also it can also help us convert a BVP to an FIE, okay, without going through the other method we just did. Okay, so if you have not subscribed to my channel, kindly subscribe to support the channel. Also like my video, comment, and also share. Okay, all right, let's start. So the Green's function, so we actually denote it by g of xt, like I've written here. And I'm giving a BVP as a second order. So in this lesson we'll just stick to second order BVP, okay? But as I'm going through the process, I'll be giving some hints about a general form, okay? But this is actually specifically for second order, and all our examples will be based on second order, okay? Alright, so if you have a BVP like this, okay, so P y prime, okay, it's a second order, this one, plus del P del x y prime plus qy plus phi of x equals 0, okay? And this is a BVP because you have the conditions at the boundary given, okay? So we have y of alpha equals k and y of beta equals z, where alpha and beta are the boundaries, okay? So we know that the homogeneous part of this is picking the parts that contains only y's, okay, and equate them to 0. This is the homogeneous part. Now the reason why we need to have this in its standard form, like the p and the dpds, we need them, okay? We need the p, especially the p, we need it. So just bear with me like this, okay? So if you pick the homogeneous part and try to factorize y out, there's a y here, okay? There's a y here as well, and there's a y here. So if I factor y from all the parts I just did, okay, what will you get? We'll get something like this. So if I factor y out, this is what I have, okay? So I have something times y equals 0. So this means that I can replace the whole of that thing by L and say that L of y or Ly equals 0. Where my L is equal to this. And now this, the important thing we should always remember in Green's function, okay? We should always know the operator. This is a linear operator, okay? So we call this the operator L, and this is the standard operator for, or the general operator for, a second order BVP, okay? So this is how it looks like, okay? So always, based on the question, you compare it to this, then you know your P, you know your dpdx, and then you know your Q, okay? So that you'll be able to use your individual P's and Q's and the rest wherever you are being asked of, okay? All right, let's continue. Now a Green's function exists, okay? So these are just simple things I did to show you what we call the linear or the operator of a BVP, okay? So I just wanted to show you how to find the operator of a BVP and its general form, especially with regards to the second order, okay? So let's go to a Green's function. Now a Green's function exists in the above BVP that we're talking about if the BVP has the trivial solution y of x equals 0. So always you should check this, always all the time. You should check that the BVP, after solving it, with our own idea of solving differential equation of the second order, okay, after solving it, then you check if it has the trivial solution, then you can go ahead and solve for your Green's function. If it has no trivial solution, then there exists no Green's function, okay? So, and there exists no Green's function if the BVP does not have the trivial solution. So some examiners can trick you. They can give you a question where there is no trivial solution. So always check that, okay? Now, steps in solving for the Green's function. So the step one is saying that g of xt is a piecewise function g1 and g2. Okay, it's a piecewise function. As the Green's function is a piecewise function g1 and g2, so it's just two of them. It's not three. Piecewise function can be g1, g2, g3 up to gn, but here it's just two. Okay, so it's a piecewise function g1 and g2 of the form of the general solution to the homogeneous part of the BVP. Okay, so let's say if I solve the BVP and I have the general solution to be, let's say y of x equals ax plus b, then it means that all the g's, the g1 will be a1x plus b1, the g2 of x will be a2x plus b2. I mean, all of them will take this form. Okay, I hope you get this. So this is what the first step says. So with the first step, after checking and seeing that the trivial solution, or the how do you call it, the BVP has a trivial solution, okay, then you go ahead and start solving for your g of xt, that's your Green's function. And the first step in that is that the Green's function should take the form of the general form of the solution of the homogeneous part. Okay, so you solve your homogeneous part and then you write your Green's function as that form. Okay, if it is an exponential function, you write it as an exponential function. If it is a trigonometric function, you do the same. Okay, now the second step is that g1 of tt equals g2 of tt for second order. So this is specifically for second order. Now in general, you do for g1 of tt equals g2 of tt, then up to the n minus 2 order derivative. So this is what I mean when let's say n is equal to 3, a third order BVP. I said that what we are doing is specifically with a second order BVP, but let's consider a case where we have a third order. Then you start doing for g1 of tt equals g2 of tt, then you come to n minus 2. N minus 2 give me what? First. So just first order derivatives. Okay, I hope you get this. So you just do n minus 2 and that will give me 3 minus 2, which is first order. So it means that I will do g1 of tt equals g2 of tt for the first one, then I'll come and do, we said up to that order derivative, so it's 3 minus 2 is just 1, so 1 is the first order. So I will do del x of g1 of tt, then it should also be equal del x of g2 of tt. So let's see if n was 4, n minus 2 and n is 4, I'll have what? 4 minus 2, which will be equal to 2. So I'll do from g1 of tt equals that, then you do the first derivative del x, then you do the second derivative del squared del f squared. Okay, I hope you get this. You do from the 0th order derivative, which is the same thing as this, then you do the first order derivative, okay, for n equals 4, then you do the second order. For n equals 2, which is our case, n is 2, so n2 minus 2 is equal to 0. So you do for the 0th order derivative, and that is the same function. The 0th order means you are not differentiating. Okay, alright, let's move on to the third point. The third point is saying that g of xt satisfy the boundary condition. So we know that the boundary conditions are that y of alpha is equal to this k, and then y of beta was also z. Okay, but you are saying that g1 of xt satisfies that. But when you see this alpha, where is it located? It's located at the or in the range of the g1. Okay, alpha is here, so you use that for the g1, and you see that g1 of alpha t. So one thing about the Green's function is that we almost all the time consider it as a function of x. Okay, so we do everything based on x. All the derivatives are performed based on x, and then the conditions are also performed based on x. Okay, so but beta is also seen in the g2, the range for the g2, so you use that one for the g2. Okay, and so you see g1 of alpha t should be equal to k. Okay, then you set one equation there like that. And then last point, you have 4 points to go. The last point is that del n minus 1, okay, del n minus 1 del s n minus 1 of g of xt at x equals t should be equal to minus 1 over p of t. Now this p of t is coming from the p we know in the operator, so the p d squared ds squared, okay, plus dp dx, okay, ds ddx plus q. So this p, whatever you have there, then you use it. Okay, I hope you get the point. So that is the p that we want to use. Okay, so minus, so if you write your p, then let's say if p is, let's say a function of x, let's say if p was equal to s squared, then p of t would definitely be equal to minus t squared, t squared actually. So you come and put it there. Okay, but here I think we'll concentrate on constant coefficients of the BVP. Okay, so when n equals 2, then if you put n equals 2, you get del of 2 minus 1, and 2 minus 1 is just 1, so del, you get just del. So del x of g of xt at x equals t equals should be equal to, okay, so here this part, everything should be equal to minus 1 over p of t. And now to perform the derivative of a piecewise function, which consists of only two functions, is the derivative of the second one minus the derivative of the first piecewise function. Okay, I hope you get this. So these are the things you should just note. So I believe you're able to know the steps. Okay, so let's pick an example and go through it. Construct the Green's function of the BVP y prime prime plus y equals x at these boundary conditions. Okay, so to solve this, the first thing we should do is, we said we write the homogeneous part, which is y prime prime plus y equals 0. And with this, you could see that you have d squared y ds squared plus y should be equal to 0. So if I factor y out, I have d squared ds squared plus 1, and y is equal to 0, which means that my L with this particular question is d squared ds squared, okay, plus 1. So we just go ahead and write our L. L is equal to d squared ds squared plus 1. So if I compare this to p d squared rather. So for the general operator L for second order BVP is p d squared ds squared plus dp dx, okay, ddx plus q. So if you compare these two, you can see that p is equal to 1, because that is 1 is the coefficient of d squared ds squared in this. Okay, this is the question, this is the operator for the question, and this one is also the general one. So you compare and write for the coefficients for the particular question. So with this question, p is equal to 1, the p ds is 0, so I don't write it, and q is also equal to 1. And the most important thing here is our p. So p is what we need, because that is what is used in the last point. Okay, so with this one, how do you go about it? We said that once you have this, you go ahead and then you solve for the homogeneous part. So with the homogeneous part, we said y prime prime plus y should be equal to 0. So solving this, what do? We said if you have a constant coefficient of a second order ordinary differential equation, then what you do is you let your solution y of x be equal to some e to the power rx. I could have written the solution, or I could have write the solution just like that, but I don't want to write it. I just want us to go through the process. Okay, and then this means that my y prime will be equal to, from this, r e to the rx, and my y prime should be equal to r squared e to the rx. So if I substitute y prime and y in this Okay, so we have y prime prime plus y equals 0. So if I put their respective functions in terms of the e to the rx and this one, okay, I have r squared, okay, e to the rx plus e to the rx, okay, and is equal to 0. This means that I have r squared plus 1 e to the rx equals 0. So this is what I have. Now I'll move forward and say that e to the rx is our function and it's never equal to 0. So this means that r squared plus 1, okay, is actually equal to 0 because I have the product of these two. I have r squared plus 1 multiplying e to the rx, and this should be equal to 0. So if I say that this part is not equal to 0, then definitely this part should be 0 because the product of these two functions or these two terms is giving me 0, and one is not 0, so obviously the other one is 0. Okay, so this means that my r, or my r squared, is equal to -1, and it means that r is the square root of -1, which is plus or minus I. So the moment you have something like this, then you know that if you have I or complex numbers, then you know that the solution is given in terms of cos and sine, and this should be equal to a constant a cos, okay, a constant a times cos of the value here in front of the I is just 1. It's plus or minus 1i, so the 1 there is what we need. So cos of 1x, so it becomes cos s, then plus b sine of 1x, okay, which is 1, which is x. So this is a general form for BVP, the general solution to this. So if a Green's function should exist, then it should take this form. So now let's go ahead and check for the existence of our Green's function. Okay, if indeed a Green's function exists, then you should be able to tell us that the trivial solution exists, or the trivial solution, this BVP has the trivial solution. Okay, let me put it that way. So you use these boundary conditions: y of 0 equals 0. So you go ahead and put it there. Y of 0 equals 0. Okay, y of 0 equals 0 means that wherever I see x, I put 0 there and equate it to 0 in this general one. Okay, so I have 0 is equal to a cos 0. Cos 0 is 1 plus b sine 0. Sine 0 is 0. So it means that a is equal to 0. So you have this as your equation 1. Okay, so we said that y of pi on 2 is also equal to 0. So wherever I see s, I put pi on 2 there. And that one, let me do it down here. So I have 0 is equal to a cos pi on 2, and cos pi on 2 is just cos 90, that is 0, plus b sine pi on 2, and sine pi on 2 is sine of 90, which is 1. So I have b is also equal to 0. So from equation 2 and 1, you could see that b is 0, a is 0, meaning that y of x is equal to what? 0, which is the trivial solution. Okay, so this means that a Green's function exists for this particular BVP, this one. Okay, so if it exists, then let's go ahead and start finding it. If a Green's function exists, then the general form of the homogeneous part was y of x is equal to a cos x plus b sine x. Okay, then we are saying that the first point is, then g of xt should take this form. Okay, it should take the form of the general solution to the homogeneous part. So it means it should take g1 of xt, okay, should be a1, okay, cos, or let me use small a, it's a constant times cos, so I can write it like q cos. The form should be the same. Okay, so let me use small a1 cos x, okay, cos x plus small b1 sine x. Okay, and we said that the range here is 0 less than or equal to x less than t. Then the second one should be a2, that's the g2 of xt, then cos t. All of them should take the same form, just that their constants shouldn't be the same. Then b2 sine x. This means that a2 and a1 are not the same. Okay, so t less than x less than or equal to pi on 2. Okay, this is what you have. Where are g1 of, okay, so if you remember in the explanation, I just wrote g1 of xt. So g1 of xt is actually the a1 cos x, okay, plus b1 sine x, and our g2 is obviously the second one. Okay, so I just wanted you to know that this is how they should be. They should look like the general form. Okay, so this is a general form for a homogeneous part, and indeed they look like the general form. Okay, I hope you get this. So let's go ahead and write the second point. The second point is saying that with the second point, where is my second point? It has this idea that g of xt should satisfy the boundary conditions. Okay, so we said that g1 of the lower limits or the lower boundary, which is a 0, okay, comma t should be equal to y of 0. Okay, and y of 0 gave us what? Y of 0 gave us 0. So it means that g1 of 0 comma t means that I just pick wherever I see x, I put 0 there for g1, well, for the x in the g1. Okay, so I'll get something like an equation to 0. So I have 0, or let's say let me put it there. I'll have a1 times cos 0, a1 times cos 0, and cos 0 is 1, plus b1 times sine 0, and sine 0 is also 0, should be equal to 0. So this implies that a1 is what? A1 is equal to 0. And then g2 of the upper boundary, okay, g2 of pi on 2 comma t should be equal to y of pi on 2, and y of pi on 2 was 0. So if I put pi on 2 in place of x in g2, I'll have a2 cos pi on 2, and cos pi on 2 is 0, plus b2 sine pi on 2, and that is 1. Okay, and this should give me 0. So this will imply that b2 is also equal to 0. So we have these as our b1 and b2, sorry, our a1 and then b2. Okay, now let's go to the third condition. The third point is saying that g1 of tt with respect to a second order BVP is equal to g2 of tt. I hope you get this. Now g1 of tt means that wherever I see x in g1 of xt, I put t there. Okay, then that is what? a1 cos t plus b1, okay, sine t. Let me write it well. b1 sine t, and this should be equal to a2 cos t plus b2 sine t. Now I realize that a1 is 0 and b2 is also 0, so you can put it there and get something like b1, okay, sine t should be equal to a2 cos t. So you can simply make one of them the subject here and put it somewhere. b1, this implies that b1 is equal to a2 cos t, okay, a2 cos t over sine t. So you put this, and let's name this equation, let's say 1 or so, because I think the previous ones Yes, these ones are not necessary. Okay, we know A1 and B2 already, so this we don't know. So we go to the fourth point and say that with respect to a second order BVP, we say that del x of g of xt at x equals t should be equal to minus 1 over p of t. Now we said our p is equal to 1, so it means that p of t is still a constant function. So wherever I see t in p, I put in, or wherever I see x in t, I put in t there. Okay, with this p, if there was an x in it, I'll put t there, but there's no x, so p of anything will still give you 1. Okay, so this means that with this particular question, del x of g of xt from x equals t should be equal to minus 1 over 1, which is minus 1. Okay, and we say that del x of g of xt for piecewise function at x equals t is equal to del x of g2 of xt at x equals t minus del x of g1, okay, at x equals t. Alright, so you do del x for, what do you call it, g2. Okay, so let me add a page. Let me write them. Okay, g2 is actually equal to, or g2 of xt, anyhow you want to call it, is equal to a2 cos x. Okay, where is my x? Cos s plus b2 sin x. Okay, and g1, okay, g1 is also equal to a1 cos x plus b1 sin x. Okay, so it means that del g2 del x is simply equal to minus a2 sin x. Okay, this one, if you want, we can actually substitute, but let me just do it like this, because I don't want a situation whereby I simplify it easy and then you don't understand. Okay, so let's go through it step by step. Plus b2 cos s. Okay, and del g1, okay, del x is equal to minus a1 sin x, okay, plus b1 cos x. So now we said that we have to do this. There's a fourth point, del g2 del x at x equals t. So minus del g1 del x at x equals t, and this should be equal to negative 1. So it means that in both this equation, let's say this first one and this one, okay, I mean this one and this one, in both of them, wherever I see x, you just put t there and you subtract them, okay, and then you equate it to minus 1. So we have minus, okay, let me use the white pen for you. We have minus a2 sine t. Okay, but if you remember, you let me write this first, sine t, okay, plus b2 cos t. Okay, cos t minus, okay, so minus a1 sine t plus b1, okay, b1 cos t is equal to negative 1. Now if you remember, a1 is 0 and b2 is also 0. So this will simply give us minus a2 sine t. B2 is 0. Okay, a1 is also 0, so minus b1 okay, b1 cos t, and this is equal to -1. So if I divide through by -1, I have a2 sine t plus b1 cos t is equal to 1. Now if you remember, let me call this equation 2. So if you remember, in equation 1 we're able to say that b1 is this. So wherever I see b1 in the equation 2, I just go and put this there. Okay, alright, so you have a2 sine t plus b1 is what? a2 what? Cos t over sine t times cos t. Okay, the whole of this is b1, and this is equal to 1. So I have a2 sine t plus a2 cos squared t, okay, over sine t is equal to 1. So the LCM here is sine t, so I multiply through by sine t, and I'll have a2 sine squared t plus, okay, a2 cos squared t should be equal to sine t. And we factor a2 out here, then I have sine squared t plus cos squared t. Obviously, you know what we are getting. This is equal to sine t. And you know this is 1, so I have a2 is equal to sine t. This means that our b1, which is equal to a2 cos t over sine t, will then be equal to a2 is what? Sine t. So I have sine t times cos t over sine t, and sine t will take sine t, so I have b1 is equal to what? Cos t. So I know a1 is 0. We know that already a1 is equal to 0, and b2 is also equal to what? 0. Sorry, yes, b2 is also equal to 0 as well. Okay, so we know b1 and we know a1, so it means that my g of xt, which is equal to, so we can write it back. Okay, we can write everything back. We know that this is equal to a1 cos t plus b1 sine t, then 0 less than or equal to x less than t, and have a2 cos t plus b2 sine t. Is it t? No, all the t's are for x, right? It's sine x, cos s, and the rest. I'm really sorry for this. Okay, it's x. All these terms are x. Okay, then t less than x less than or equal to pi on 2. So this is what we have. Now you know our a1 to be equal to 0, our a2 to be equal to what? Sine t, right? If you remember, this is our a2, and our b1 is what? Cos t. b2 is 0, so b1 is cos t, and b2 is what? 0. So this means my g of xt, which is the Green's function, is finally given by, okay, is finally given by a1 is 0, so the first part to go. b1 is what? Cos t, so I have cos t sine x, cos t sine x, then the range is 0 less than or equal to x less than t, and then my b2 is 0, my a2 is a2 is sine t, so I have sine t cos x. Okay, I have t less than x less than equal to pi on 2. So this is very simple, right? Just that it's very lengthy, but I know you cope with me. Okay, so this is the Green's function for the BVP we stated. That is the BVP y prime prime plus y equals x. So you see that the x didn't play any role in constructing the Green's function. Okay, so we'll use the x later, but then that will be in the next video, which will be using the Green's function to solve a BVP. Okay, all right, so thank you, and don't forget to subscribe to my channel if you have not subscribed, and see you next time. All right.